Hey, it's Leo. Today we're going to talk about this interview question asked by LinkedIn and Facebook. We're given a graph of n nodes labeled from 0 to n-1 and a list of edges that connects to two nodes together. Notice that we're talking about undirected edge here. We need to return true if the given edges make up a valid tree and false otherwise. If you are familiar with the graph, a graph valid tree is defined by the first, all nodes are connected, and the second, the number of edges is equal to the number of nodes minus 1. For the example, let's say we have the edges like this. We can draw the graph by linking 0 to 1, 0 to 2, and etc. Notice that we are talking about undirected graph, so there's no arrow between the edge. Apparently, this is a valid tree that all the nodes has its parent node 0. If you're looking for the other example, given edges like this, you'll find a cycle in the graph. And we know that the valid tree cannot allow the cycle, so therefore return false. In order to determine the input array is a graph valid tree, the first it's converted the edges into the graph. Initially, we can declare a graph dictionary variable that has all the nodes as a key, and the value is just an empty array. Because we are talking about undirected graph here, so the edges 0 to 1, that means from 0 we can go to 1, and from 1 we can go to 0 as well. Eventually, by scanning all the edges we have, we can come up with a graph variable like that. The next step is to find if the graph has a cycle. The common techniques we can perform is BFS or DFS. Additionally, we can use union find, which is a more advanced technique. I will talk about this later. We know that in BFS we have the stack variable that we add nodes and pop nodes. But because we are talking about undirected graph here, we need to introduce another variable called parent. The parent variable is a dictionary that the key is the trial node and the value is the parent node. From the BFS, let's first add the node 0 into the stack. For the parent node, let's just initialize the parent of the 0, it's minus 1. Notice that this can be changed later by going through the other edges. By popping 0 from the stack, we'll now traverse the neighbors of 0. So we have 1, 2, and 3. We add them together into the stack. We know that 1, 2, 3 are coming from node 0, they are neighbors of node 0. So the node 1, the parent of node 1 is 0, and the parent of node 2 is 0 as well. As we are popping 1 from the stack, we know that the neighbor of 1 can actually go to 0 and 4 because it is undirected graph, so it can actually goes back to its parent. Because we already marked the parent node of 1 is 0 in the parents variable, that prevents us to go back to 0. So at this time, we simply just mark 4 into the stack. Now, how do we use BFS to find if the graph has a cycle? Let's say we have a graph like this. The first is to add 0 on the stack. Initially, we mark the parent of 0 is minus 1. As we are popping from 0, we have the neighbors 1 and we add it to the stack. We mark the parent of 1 to be 0. As we pop 1 from the stack, we're now adding the neighbors of 1, which is 2, 3, and 4 on the stack. Because they're all coming from the parents node 1, so we add the following to the parents dictionary. And then we pop 2 from the stack. We know its parent node is 1, so it won't go back to 1. We'll add number 3 to the stack. As we're popping number 3 from the stack here, we know that the parent of number 3 is 1, so it won't go back to 1. But it will add number 2 on the stack, and we realize number 2 has been visited before. It appears in the parent as the key. So now that creates a cycle. Here's the Python code. At first, we need to check if the number of edges is equal to n-1. If it is not, return false. And the next step is building the graph. I initialize the value inside the graph as an empty array. Because it is undirected graph, so I need to append from index 1 to 0 and 0 to 1. And the second part is the BFS approach. I add the parent of 0 to be the minus 1. Just as the starting point, because we need to check if all the nodes they're connected. So at the end, we need to return if the length of the parents is equal to m. If they are less than, that means we didn't go through all the nodes, so we will return false, otherwise we return true. The time complexity of building the graph is OM, that means the number of nodes, because we need to go through all the nodes. The time complexity for BFS is the number of edges, because we need to go through all the edges. So the total complexity is the number of nodes plus the number of edges. Alternatively, we can use DFS. In DFS, there's no need to store the parents into the local variable. They actually save us the space and complexity. In the recursive function DFS, we can actually bring the parent as the parameter of the function into the next iteration. So let's say we are on the node 2 here. The DFS recursive function will become 2 and 1 because we know that 2 it's coming from 1. Another way of solving this question is that we can use this advanced algorithm called union find. Initially, suppose each node is an individual set. By going through the edge, we know that 0 is connected to 1. So that means we can actually add the set 1 into 0. It becomes 0 and 1 together as a set. On the second edge, we know that 2 is connected to 0. And 0 is in the set 0 and 1. So now we're adding the set 2 into the set 0 and 1. That becomes... In the end, we have the set that has all the nodes together. And there's no node that is left. So now we have a whole valid tree graph. Apparently, let's say if we don't have the edge 1 and 4, that means the set 4 is individual, it's not connected to the big set. Eventually, we have 2 sets. So that means all the nodes, they are not connected. On the other hand, if we're looking for the graph that has cycle, at first, we are building 0 and 1 as a set. Next, we are adding 2 into the large set, so we have 0, 1, 2. And then next, we are adding 3 into the set, so we have this. At fourth, now notice that we are adding 1 that is already in the set, and 3 that is already in the set either. So that means we have a cycle. And here's the Python code. Notice that while merging the set, we need to pop the element from the set 2 and add it to the set 1. So let's say we are adding 0 and 1 together, we need to pop 1 from the second set, so the second set is gone. As I just mentioned before, if on the edge, the first element and the second element, they are all existing in the set, that means we have a cycle, so we need to return false. So far, I know that playing with the set, it's kind of like a waste of time complexity and space complexity. Is there any way we can improve this? From the previous example, BFS and DFS, we utilize the parents node. In this time, we can actually combine the parents nodes with the union find algorithm. By converting a set like this in the graph, we can actually just treat all the nodes. It has only one parent, that's 0. And here's how the algorithm works. Suppose we are only dealing with the parents variable. Now, by scanning the edge 0 and 1, we can say the parent of 0 is 1, so we change this to 1. The edge 1, 2 means the parent of node 1 is 2. And edge 2 and 3, that means the parent of node 2 is 3. As we are scanning to 1 and 3 again, now we are about to change this value to 3. However, we know that the parent of node 1 is 2 and the parent of node 2 is 3. So 2 here, that actually means 3. And now we find that this graph is a cycle. Now, how do we implement the function to find the real parent of the node? Because in this time, the real parent of node 1 is actually 3. We can use while loop in the function. So let's say we are on the node 1, while the node 1 is not equal to the parents of node 1, which is 2. We assign the parents of node to this node. So now the node becomes 2. At node 2, we have the parents that is 3. So we assigned 3 to the node. And now we are on the node 3. We know that the parent of node 3 is 3. So finally, we return 3. And here's the Python code. Again, we need to use the find parent to find the real parent of the edge at index 0 and 1 so that we can do the comparison. Now you'll notice that here, if I assign the edge 1 as the parent of edge 0, why do I need to find the real parent of edge 0? If you're looking for this example here, at first, we assigned node 1 to be the parent of node 0, and that's not a problem. While we are assigning the node 4 as the parent of 0, we cannot just replace 1 to be 4, because that will lose the connection of 1 and 4 as well, right? So as we are going back here, while we are adding 4 to 0, we need to actually find the parent of 0, that it's 1. So we are adding 4 to the edge, to the node 1 here. If you like this channel, please click like and subscribe. Thank you.